Okay. Oh, something is. Okay, can you hear me up there? It works? Yeah. Okay. So we made it to the last lecture of this class. So this is just to remind you that next Monday we have a poster session. Everyone is welcome, even if you don't have posters. So we're going to set up easels in the morning, 8:30. So please be ready at 9. As I said, we probably have something like 3 minutes per poster, which hopefully you'll be able to do a few times for me and for the TAs. But if I want to go over all the posters, it basically means 3 minutes. So be ready with your 3-minute spiel. Basically, that's it. Questions? Yeah.
Are you providing poster boards?
Yeah, there will be poster boards, and we suggested, I think it's on the web and on Piazza, the simplest thing would be just to print 8 slides or something like that. That would fit. I think the size is on the Piazza note, but I think 8 slides.
Put it on like that day. We'll just put it on that morning.
Yes, put it on that morning. So we'll have all the equipment necessary for that. Yeah. So it's just that if you really want to print a poster, you can. Only that 1, it's expensive. 2, it takes time. So if you want to do it here in an organized way, they wanted us to give you to give them the posters, I think last Monday or something like that. So they need a few days. So it's probably best to just print slides. Other questions? Okay, so where are we? So we are talking about Bayes nets, specifically learning Bayes nets. and we agreed that we learned about this. We talked a little bit about inference, and we want to get to the learning problem. So, okay, where are we? There's a lot of things here that you can see that I skipped. Learning problem. So we had to talk about the inference problem because in order to do the learning problem, we need to be able to do inference, which means we have to compute the probability of an event given the Bayes nets. But now we are at the learning problem, and this is kind of where we ended last time. We're given a problem, given data, n tuples. For now, or for the end of last time, we assume that these are sampled from a tree-dependent distribution, and we understand what that means. Basically, it's a generative model. And our goal is to find a tree-dependent distribution, a tree representation of this distribution, and we already discussed what that means. I mean, we are really thinking about it from the perspective of most likely tree. So, basically, that's what we solve. The most likely tree is the argmax over all trees of P probability of the data given the tree, using the basically Bayes rule and maximum likelihood. And we assume, as always, that the data points that are given to us are independent. Okay, so what we've done at the end of last time is we looked at an example. We looked at 3 probability distributions. This is one, just a table. This is another one, where once I'm giving you these conditional probability tables, it's a well-defined probability distribution, and this is a third one. And we asked 2 questions. One question we asked, are these representation of the same distribution? And we discussed what it means to determine whether 2 representations are the same probability distribution, yes or no. And we also discussed the question of, given a sample, a collection of data points, which of these 3 generated it. And the answer to this is really which of these 3 is more likely, or the most likely to have generated it. And we actually answered this at the end of last time. So the first thing is we looked at this data. These are the 3 data points that we have. And you thought that this probability distribution definitely did not generate this data. And the reason is that one of the data points, it's the 1011, this one here, is not supported by this distribution at all. So this distribution couldn't have generated it. So we've written it as the likelihood of this distribution is 0. And then we computed the likelihood of each one of the other distributions to have generated the data. And the way to do it is, first of all, to make this distribution concrete. So I have to give you numbers, and the numbers I have to give you are P of x4, which is the root, which really is 2 numbers, but 1 independent number. And for each one of these edges, P of x1 given x4, x2 given x4, x3 given x4, I need to give you 2 numbers. So here I'm writing it as, given that x4 is 0, I'm giving you P of x1 being 1, x2 being 1, x3 being 1. And you also know what is the probability of what's the probability P of x2 being 0, given that x4 is 0, just 1 minus this. And similarly, I'm giving you the conditional given that x4 is 1. So these 7 numbers are the 7 independent numbers you need to define this distribution. And given that, we computed the probability of each of the data points. So, for example, you can look at the computation here. We have to compute. Could you sit down? Thank you, because you're blocking the projector. P of x4 being 1, x1 being 1, given that x4 is 1, x2 being 0, given that x4 is 1, and x3 being 1. Now notice that I did not give you this probability. P of x2 being 0, given that x4 is 1, but I gave you this one, which is 1 minus it, and therefore you see the 2/3 here. Okay, so this should be simple to follow, and we computed the probability of the data given the tree, which we have to maximize if we want to know the probability, the most likely tree given this data, and we did the same thing for the second tree. Again, you just have to make sure that you understand that these conditional probability tables are sufficient to determine this as a probability distribution, and once we have this, we can compute it, and we conclude that the distribution 2 is more likely to have generated the data. So we ended last time with the agreement that we've solved this problem before in a slightly simpler instance. It's really the same as tossing a coin, looking at a few observations, and determining which of two possible biases is the correct bias of the coin. Questions so far? No questions. Okay, so now we want to solve the real problem, and the real problem is all trees are possible, not only three distributions. And how do we do it? So, we also discussed the fact that there's no target distribution. We cannot talk about the target distribution. We are really talking about the most likely one. So here are 3 data points. And really what I want to know is I want to be able to compute the probability of various events. So, for example, I want to know what's the probability of 1, 1, 1, 1. That means x1 equal 1, x2 equal 1, x3 equal 1, x4 equal 1. Or I want to know, I'm using this notation here to denote that I want to know the probability, for example, here of x4 being 0. Or x1 and x2 being 1. Now, I could use the data to do it. Right? So what is the probability of x4 being 0 if all I do is look at the data? What? What was it? 1 over 3, yeah. Now, is this the right thing to do? What is the probability of this event? 0, because none of the data points satisfies x1 and x2 being 1. Now you can do this. The issue is that this is also making an assumption. What is the assumption that we are making here? The assumption that we are making here is that the support of the distribution is only on these 3 data points uniformly, and that's it. The support on the rest of the data is 0, which doesn't make sense, right? Doesn't make sense because you actually have seen a very, very small sample. And this will always be the case in realistic situation, even when you have more than 4 dimensions, like here, you will always see a very small sample of the data, so you want to make assumptions. And the assumptions will allow us to compute the probability of these events even for data points that we've never seen. And this is really the same game that we'll be playing throughout the semester, so I'm going to remind you this in the last slide today, but if you think about it, it's the same point that we've made in the first lecture when we talked about the badges game, where we looked at the badges, and I told you, here is one hypothesis. This was the data, the paper that I gave you, right? So this was a hypothesis that you can use. It basically puts all the support on the names in the list, zero support outside. It's a hypothesis, right? You can use it to make predictions, but it's not so useful. Really what you wanted to do is to make assumptions that will allow you to make predictions on data that you've never seen. And that's what we're going to do. So we're going to make the assumption, some assumptions on the distribution, and specifically here we're going to make the assumption that we want to learn 3 dependent distributions. So we can actually formulate this problem in a couple of ways. Here is one that we actually hinted on before. Given data, assume to be sampled from the 3 dependent distribution, find the most probable tree that has generated this data, right? The most probable tree representation of this distribution. So that's one problem. In fact, we will be able to solve a more general problem. Again, given data, the difference between given data here is that I'm saying given data assumed to be sampled from a 3 dependent distribution, and now I'm just saying given data. I don't know where it's coming from. I don't know what type of distribution has generated it, but I'm going to learn it using a 3 dependent distribution. So what I'm going to produce in the output is a 3 dependent distribution, one that best approximates the distribution. So I'm not just making any assumption on where is the data coming from, but I have a hypothesis. My output representation is going to be a tree. And remember that we've actually done the same exercise also when we talked about discriminative learning, right? We started by saying, I know that this data is linearly separable, or I know that this data is represented using a specific function of a family of functions, and we're going to learn into it. And then toward the end, we called it agnostic learning. We said, I don't know where the data is coming from. I'm going to use linear functions to learn it, or I'm going to use, neural network of depth 2 to learn it. So pictorially, you can think about it this way. So let's assume that this is the space of all 3 distributions. In the first assumption, I'm assuming that this is the target distribution. It's an element in the space of all 3 dependent distributions. In the second case, I'm looking at the space of all distribution, much larger space, and it's possible that the target distribution is somewhere here, but I'm going to learn an element here, and hopefully the one that is closest to it in this space. That's my goal. Okay, so now we're going to start learning, and again, the tool that we have is this, maximum likelihood, and the question is, how do we do it? So again, if you look at this picture, we need to have some technical notions here. The first notion that we have to have is a distance between distributions, because I want to find a distribution that is the closest, that is a tree, and is the closest one to the one that we found. So I need to define a distance between distribution. Now, if you think about it, the notion of distance between distribution is a relatively simple one. What is a distribution? Just a function, right? It's a function that ranges from 0 to 1. So you can think about, okay, let's assume that this is my domain. I have one distribution here. I have another distribution, and I'm looking for the distance. So you can look at the point-wise, at each point, what is the value of distribution 1? What is the value that distribution 1 assigns to it? What's the value that distribution 2 assigns to it? And you can look at the difference and sum, and you'll have some distance between this distribution. However, we are going to do something else. So we are going to define a distance measure that is called the KL divergence. And the reason is that this is the right one to use in this specific case. How do we define it? Again, it's a relatively simple definition. So the distance between probability distribution P and 2 is defined as the sum over all elements in our domain X, P of X log P of X over T of X. So really this is not a distance. Nevertheless, it's called sometimes a distance. The important thing for us, and you can think a little bit about why this is true, is that it's non-negative and it's 0 only when P and T are equal. And as I said, it's not really a distance. It's not a symmetric function. That's one. The second thing we want to discuss is we're going to learn a tree. So we're going to have a bunch of nodes, the variables, and to make it a tree, we have to decide which edges to connect. So we need some scoring function for edges. What is the appropriate measure for edges? And it turns out that the importance of edges is going to be, again, depending on the fact that we call this scale divergence, is going to be something that is called mutual information. So we're going to define the mutual information between two nodes, X and Y, this way. So again, we have a probability distribution, and as a function of P, we define the mutual information between X and Y to be the sum over all pairs, P of X, Y, the joint distribution, times the log of P of X, Y divided by P of X, P of Y. So you can see that this is related a little bit to independence. And this is something that, given data, we can estimate. Okay, so now that we have these two components, we can start learning. We can start the learning algorithm. So we're given m independent measurements sampled from our target distribution P. First of all, we're going to, for each variable, we're going to estimate P of X, n numbers. Then we're going to estimate P of X, Y, n square numbers. Already here, by the way, it's important to realize that you should think about scaling this. So when you did naive Bayes, even though in some cases it took you time, what took time in running naive Bayes? What?
Training.
What does it mean, training? But what really took the time?
Getting through the documents and each document.
So really the feature generation took the time, right? Once you generated the features, computing the statistics, you computed basically n statistics, right? Where n is the number of features. What would have happened had you needed to compute n square statistics? So think about the case where you have 100,000 features. How large is n squared? 10 to the 10. But yeah, large number, right? So even this simple algorithm may not be realistic for space considerations when you have very large dimensions. Naive Bayes is still realistic because it's linear. But anyhow, we're going to keep on doing this. Just keep this in mind. It's an important issue. For each pair of variables, now I have P of X, I have P of XY. I can compute the mutual information. Now that I have the mutual information, I can learn the structure. So I'm going to build a complete undirected graph with all the variables as vertices. Okay, so I put all the variables, now I build a tree on them. How would I build a tree? I'm going to put the mutual information on edges in this click, and then find the maximum weighted spanning tree on this. So just to remind you, I'm sure you've all seen what is maximum weighted spanning tree. So what is the algorithm for maximum weighted spanning tree? Basically a greedy algorithm that, given that I told you I of xi is the edge, is the weight of the edge, we can continue this way. So basically our goal is to find a subset of the edges that form a tree. It's going to include each of the vertices, and the total weight of the edges should be maximized. So the way to do it is basically go greedily. I'm going to sort the weights. Again, the weights are the mutual information of the pairs. So I have n square numbers. Start greedily with the largest one, add the next largest as long as it doesn't form a cycle. If it does form a cycle, discard this weight, move on to the next one. At the end of this, it's easy to see that this is going to form a tree. It's a spanning tree in the sense that it touches all the vertices, and it's not easy to see that this is the maximum weighted spanning tree. So the complexity is n square log n because I touched n square edges and I had to sort them. So now I have the structure. So we can go back to the algorithm. I built a maximum weighted spanning tree. I have the structure. Now I have to make this a probability distribution. So first of all, I'm going to make it a directed tree. To make it a directed tree, I'm choosing randomly a root variable, and I'm going to direct everything away from it. That's a simple way to make an undirected tree a directed tree. And now I have to make it a probability distribution, which, if you want, we've learned the structure. We talked about it last time. We have to learn the structure and we have to learn the numbers. And I'm going to put numbers on the edges, and the numbers I'm going to put on the edges are basically the conditional probability of the edges. So if I have an edge directed from x1 to x7, I'm going to put there the conditional probability p of x7 given x1. So now I have a probability distribution. Yes?
How did you choose the root?
Randomly. So of course,
For you to get the...
yeah, so good question. So there are many questions here, right? So in fact, there are three questions. One is, at least the order that I have here is, why did I place the conditional probabilities on the trees? I already have some numbers there, right? Mutual information. Why won't I use this? Or any other number? So basically, how do I solve the learning the numbers problem once I have the structure? And I solved it in one here by placing the corresponding conditional probabilities from the data on the edges. And I'm claiming that that's the best thing to do. Two, why is it that sorting by the mutual information is the right thing to do? Right? So I build spanning tree. I put the mutual information as the weights. Why is this the right thing? So there are so many structures I can choose from, and I chose the one that is the spanning tree with mutual information on the edges. And three, which is your question, is why does it make sense? I mean, why choosing a random root and directing everything away from it is the right thing, right? So you can imagine many other ways of doing it. And basically what I'm saying by choosing it randomly is that all these trees are going to give me the same probability distribution, right? Because I didn't tell you how to choose. Choose this. You're going to choose edge number 1. You're going to choose n number 7. So node number 7. And I'm claiming that you're going to get the same probability distribution. So what we're going to do in the next few minutes, or until the end today, is basically justify this. I'm going to justify 1 and 2, and in your homework, you're going to justify 3. and I'm going to give you an example at the end that will help with that. So basically, in order to show that this makes sense, we have to justify 1, 2, and 3. And really the reason I do it is because each one of them has some lessons that will give you some technical tools. So basically the first one is really the learning the numbers question, right? So believe the structure for now, believe that I learned the right structure, and I'm going to show that placing the corresponding conditional probabilities on the edges, the empirical conditional probability, is the right way to make this a probability distribution. So what is the problem we're having? Given a tree, T, the structure is given to us, defining probability distribution, capital T, by forcing the conditional probabilities along the edges to coincide with those computed from the sample, gives the best tree-dependent distribution. That's what I'm showing. Okay, so let T be the tree-dependent distribution according to the fixed tree that we have. We know what's T of X, the probability distribution. It's the product over here. Again, remember that I'm using the notation here because I'm assuming that for one of the nodes, the set of parents here is empty. It's just easier to write it this way. I'm going to use the distance between P and T, and I'm going to show how to generate T so that this distance is the smallest possible, right? So, okay, so this is again the question, and we have to do some algebra. So what is the distance between P and T? It's defined to be the scale divergence. I lost this. Sum over all data points, P of X log this ratio. I'm writing this down this way. So it's, in both cases, sum over X, P of X log P of X, minus P of X log T of X. Now notice that this is the negative entropy. We've seen entropy before, couple of months ago in decision trees, but it's the same notion. I have a discrete probability distribution, and this is the entropy of X, entropy P of X if you want. And I'm left with this, sum P of X, and I'm writing this more explicitly. So T of X, as we said, is the product T of Xi given parent of Xi. Taking the log, this becomes a sum over all variables, log T of Xi given pi of Xi. So, and again, I'm reminding you that I'm abusing the notation a little bit here. So when is this maximized? So basically the question is, how should I define T of Xi given pi Xi so that this expression, this is maximized or the distance is minimized? Yes?
Is T of X the probability that?
Yeah, T is the probability of the tree. That's my notation. So remember, as we said it before, T of X is this, okay? So it's basically the probability of the tree. And I don't know this, right? So that's what I want to define. I just know I'm calling the probability of the tree T of X, and I'm defining it as this, but I don't know how to compute this yet, right? So I have just a structure. I have to put this conditional probability somehow, and basically what I'm going to show is that T of Xi given parent of Xi should be P of Xi given parent of Xi, where P is the empirical distribution, the sample that I got. Okay, so here is where we are. I already showed you the first two lines. This one was just the definition, and here I replaced it by entropy, the first term, and I just opened this. Now notice that this is, I'm going to carry the entropy here all the time, so we can forget about it for a second. This one is basically an expectation, right? So this is an expectation according to P of this. So I'm writing it expectation according to P. of this expression, which is basically sum over all my variables. Now expectation is linear, so I can, expectation of the sum is the sum of the expectations, so I can write it sum over all variables, expectation of P, expectation according to P of this variable. And what is the definition of expectation? Basically, again, I'm leaving the sum here. And here I'm just writing the definition of expectation. It's the sum over all variables. It's according to P. So it's P of xi, comma, pi of xi, value of this variable. That's just the definition of expectation. Now I can write this P of xi, comma, pi of xi as P of xi given pi of xi times pi of xi. So I'm writing this again as P of xi given pi of xi times pi of xi. I wrote it outside because really this is the sum over pi of xi. So I just need this here. And the sum of xi doesn't matter for this. It's a different variable, right? Pi of xi is one variable, xi is another variable. So basically I can split it this way. And that's the term that I care about. Now the question is, when is this going to be maximized, right? So notice that what I have here is basically sum over variables. And I want to know what should I put in T here so that this expression is maximized. And I'm going to argue that this happens when I substitute for T, P. Yes? So to see this, really what you can do is you can look at the difference between these two, and I'm going to write it here now. So if you look at the difference between the expression that we have and the expression that we have with P, what I did is I just substituted for the T, P. Notice that this is just another expression for KL divergence. This is just the KL divergence dPT, where it's the conditional probability distribution that I have here, but still it's a KL divergence between two distributions. And we know that this is zero only if and only if the two distributions are the same. Otherwise it's non-negative, and therefore the best value we're going to get where for T I place P. So what have we shown here? Okay, what have we shown? We basically gave an algorithm for learning the numbers given the structure. We've said if someone gives you the structure of the tree, but in general it's going to work for a base net in general. If someone gives you the tree, what you want to place on the edges is the conditional probability from your sample. That's going to be the best thing you can do. Yes?
We could have also derived that from maximum likelihood estimate, right? We could have just written so we know the parameters.
Yeah.
We know what we want to maximize.
Two.
We just differentiate that with respect to the parameters partially.
Yes, so basically what you're saying is that you can show that the maximum value of this is accepted where I substitute T for P using calculus. Is that what you're saying?
I'm talking about maximizing the probability of getting the data given the parameters. What we did in the maximum likelihood estimate. We know the parameters once we know the structure.
Yes, okay, so you want to set, so first of all, I think you're right. I mean, so you can say, here's my data, what are the parameters that maximum the likelihood of this data, given that I have the structure also, and then you will get that T has to be P. Yeah, you can do it this way also, right. I think it's going to be more work than this, but you can try, yeah.
But it will go very similar to the base.
It's just like we've done in naive Bayes and in the coin. It's exactly the same principle, yeah. Okay, so the next one, that I want to show is, I want to show how did I choose the structure. And remember, the way I chose the structure was actually very simple. I just placed mutual information and then find the heaviest tree where the edges have this mutual information on them. So maximizing the sum of the mutual information is the best thing to do to minimize the distributional distance. So I've already written this before. I've expressed the distributional distance this way, entropy minus this sum. I'm going to rewrite this expression here. This log p of xi given the parents. Now, what is p of xi given the parents? I can write it as p of xi and the parent divided by the probability of the parent. Right? So it's this divided by the right side of the denominator here. I'm also dividing and multiplying by p of xi. So I divided by p of xi, and I multiply by p of xi, but I already took it outside of the log, so I kind of skipped the step here. Right? But again, so this one, the numerator divided by the right side of the denominator is exactly what's written here. And then I divide and multiply by p of xi to get this expression. And the reason I want to do it is because now I want to multiply both sides of this by p of xi, comma, pi of x, the parent. So I did this in both cases. A little bit of algebra. So what is this? Okay, so the h, I just copied the h. This now is just the mutual information expression between xi and its parent. And here, actually I'm cheating a little bit. I'm summing this, with a little bit of algebra, you'll be able to see that this is equal to this. I'm cheating here a little bit. Okay, so first of all, I'm saying that because I have this sum here, this one is just a mutual information. And the orange one requires a little bit of algebra, so let's skip this for a second. The important thing that I see here is that you have three terms. Two of the terms do not depend on the tree structure. Only the middle one depends on the tree structure. It cares about xi and its parent. The others have nothing to do with the tree structure. And therefore, minimizing is equivalent to maximizing this. Minimizing the distance, dpt, you will get by maximizing this expression, which is what we've done. So essentially what we've shown is that there is a very simple, greedy way to choose the best structure. You don't need to touch all the possible trees. All you have to do is to place mutual information on the edges and choose the heaviest tree with these numbers on the edges. Yeah.
Are you assuming here that xi and pi of xi are independent?
No. Why should they be independent?
How did you get the middle term exactly?
So this is just the middle term, right? So let's look here. So, okay, I'm starting with this. xi given pi of xi. I'm writing it as p of xi and pi of xi divided by p of pi of xi. Always true. Now I'm taking this and I'm making one more step. I'm taking this expression, dividing it by p of xi, and multiply it by p of xi, so I'm getting this because it's under log. That's it. So this is just algebra. Now, remember, this was this expression here. So I'm going back to this expression and I'm multiplying everything by this guy. So that's what I've written here. I took this and I multiply it by this expression. So I get this. When I sum everything, right, I have to sum with the sum, this is just the mutual information between xi and its parents. Okay? By definition. So you'll have to go over it and make sure that you understand the algebra, but really it's relatively simple algebra. So it all goes from the definition. Okay. But the bottom line is that earlier we solved learning the parameters problem. Now we solve learning the structure problem. Right? We show that the structure of the tree, undirected at this point, you can get the structure of the tree without touching many trees, just by computing the mutual information and maximizing it, finding the tree that maximizes the sum of the mutual information over edges. Now, by the way, this is something that works very nicely for trees, isn't going to work so nicely for general structure. There, you have to do search. You have to touch a lot of trees, a lot of structures, and figure out which one is more likely. And that's why trees are so nice, or probabilistic trees are so nice, because everything is much, much simpler. Okay, so basically we solve this problem without any need to exhaustively touch all trees. Okay, so now this, some history. Or in fact, before that, let's talk a little bit about part 3. So part 3 is, we have now an undirected tree. We want to make it a directed tree. Once we have a directed tree, part 1 already told us how to make it a distribution, but how to make it a directed tree. So I'm claiming that I can transform the resulting undirected tree to a directed tree just by choosing any root variable, any variable to be a root, and directing everything away from it. So basically the claim is any node that you choose is going to give you the same probability distribution. So we already discussed last time what does it mean to get the same distribution. So you know this answer, and so in the homework you'll basically prove that regardless of the node you choose, the distribution that you will get is always going to be the same. I'm going to give an example in a second, but you will have to prove it. So now, what have we done? If you believe 3, we learned the best tree-dependent approximation of a distribution. We don't know what is the original distribution, but we learned the best tree-dependent approximation of it. Now, this is actually, just like a lot of things we've done in the class, it's an old algorithm. It's really an algorithm that's called the Chow-Lu algorithm, proposed by information theoretic people Chow and Lu in the 60s as a way to compress data. Was adapted by Judea Pearl, where he invented BaseNet, or kind of studied all the computational theories of BaseNet in the early 80s, I think, or mid-80s. Since then, it's been invented a few other times and generalized and so on, but still it's a very cool algorithm, very simple algorithm to learn something quite expressive. Okay, questions? Yeah.
So the fact that choosing any random node gives you the same probability of getting the data, it's sort of unsettling. Because I was thinking of an example where suppose you have just one edge, 2 nodes. So one is that an earthquake occurred, and the second is a building fell down. If you have some data for this, you can just make the edge go other way around, that the building affects the earthquake, and you will get the same data.
Okay, you'll have to write this down and convince yourself that this is the case. I'm going to give an example, and maybe the example, well, it will not be a proof, but it will already convince you a little bit. So let's see. So I'm going to run the algorithm. I'm going to change it a little bit to simplify my life, but we have 3 data points, the same data points we had before, and I want to learn the best tree probabilistic tree given this data point. First of all, I'm estimating the parameters. So I'm estimating P of A, B, C, and D from the data. That's what we have here in the first row, right? So that's the first thing that I have to do. Then I have to estimate all the pairs. So I'm estimating here all the pairs, P of AB, AC, AD, and so on. That's what we have, just 6 numbers in this case. Now I need to compute the mutual information. So first of all, I'm computing these ratios. So you will check, hopefully I did it right. Now I need to compute the mutual information. I did not compute the mutual information. Basically, I did not do the logs because it was gonna look ugly here. So I took the log out and just gave you numbers. It doesn't matter for the sake of this exercise. It's nicer to look at these fractions than to look at the log. But basically what you have here is the IAB is without the logs. But assume that these are the real mutual informations, and now we can do the learning. So once I have all the parameters, what do? I have to generate a structure, the undirected structure. Right, so which one is the largest here? So I think 9/2 is the largest here. So, but I have several of them. I'm going to choose AB, for example. Okay, I'm just reminding you that this is the mutual information and that I cheated, I didn't take the log here. So I chose AB to be the first edge in my spanning tree algorithm. Now I have to do something that is connected to A or to B and is large, and let's see, I chose AD, it's 9/2 also. I could have also chosen BD, it's also 9/2, but I chose this one. And now I can continue, and I'm choosing this one. A to C, it's 15/4. So now I have a tree. Okay? I have an undirected tree. The next step is to direct it. Now, as I said, I have several options here. Right? So, just to, I don't think I have it here. So I have can you see? So what are the options that I have? One tree is going to be B going to A, going to D, and going to C. In this case, I chose B. I can also choose A. So I'm going to have B, then I'm going to go to D, and I'm going to go to C. And there's a few other options here, right? 2 other options. So my claim is that, now it looks different. My claim is that these are the same probability distribution. Now remember that I'm not done by doing this. What else do I have to do? I chose the directions. I have to compute the numbers. So what are the numbers that I'm going to compute here?
P of B.
P of B
P of
here.
A given B.
P of A given B.
P of B given A.
And here I have to do P of C given A. On the other hand, here I have to compute other numbers. Right? So here I have to compute P of A. I didn't know it there. I didn't compute it there. Here I have to do P of D given A, P of C given A, and P of B given A. So you see, it's different conditional probabilities, and this is where the secret is. Right? So because it's different conditional probabilities, the different structure with their corresponding conditional probabilities here is going to give exactly the same probability distribution as this structure with the corresponding probability distribution. And this is what you're going to write down and convince yourself of in homework 5. Questions? Okay, so let's summarize. So basically what we've done is we ran this Carlo algorithm that maximizes the likelihood of the data, or that found the tree that maximizes the likelihood of the data. Now, we didn't talk about sample complexity, you know, how many examples are needed and so on. This is a little bit less important, but really we have an algorithm that knows how to learn a distribution. And again, a distribution in this case means structure and numbers. And I want to kind of close the circle with the same comment that I had before. So notice that what we are doing here is we're taking statistics to estimate the probability of events so that we can generate the trees. Once we have a tree, we're going to use it to estimate the probabilities of other events. Right? So we basically, what we care about is evaluate the probability of other events, this last line there, but we are doing some intermediate calculation, sometimes difficult calculation, by inducing this model, which itself we do by estimating some probabilities. In this case, you know, these conditional probabilities, and on the way to do this, we also computed the mutual information and so on. So again, you can ask yourself, why do I need this? I mean, why don't I just use the raw data? I have raw data. You want to know the probability of some event, just use this. And in some sense, this is kind of the basic question of this class, right? So it's the same question that we've done. I asked this when we talked about the badges. I reminded you a few minutes ago with these slides here. And essentially, the reason is that you need to make assumptions in order to get something. If you just use the data, it's too sparse. It's not going to give you information. It also is making some assumptions. If you decide to use just the data that you've seen, you are making some assumptions, only that maybe you're not making them explicit. You're making the assumption that that's it. There's no other data outside it. Everything else is not supported by the distribution that governs the generation of the data. While if you make some assumption on there is a model that has generated this data, like what we've done here, then you know that there's other data out there that could have been generated. You just haven't seen it. And that's basically what we've done here, and in fact we've done throughout the class. So, so that's a good way to end what we are doing. Questions? Yeah.
So while those two trees both represent the same distribution, because the numbers that we're representing each node are different, the probabilities, assume that the data did come from the left of the two, and that was the true way the data was generated. Won't that tree be more helpful to us when trying to calculate events than the right tree will?
No. I'm claiming more than what you said. It's not that this is the same as this because the numbers that I have to compute are different. This is the same as this. It's exactly the same probability distribution. So if you sample data, the likelihood of a specific data or set of data to come from this is exactly the same as here. So basically you will have to prove that the distribution that I'm writing here, once I place numbers here, is exactly the same as the distribution here. So it's not that they look similar, or it's exactly the same function. So it will require a little bit of algebra, but it's actually relatively easy to do. So it's magic, but yeah, you have 4 options here, and they're the same. Other questions? Okay, so I'm going to see you on Monday for the posters. If not, on the 19th in Town 100 for the final. And other than that, have a good break. Okay, see you. Thank you. Sure.
So we need to, for example, we have a data and we need to prove that the probability generate this data from this tree is the same as this tree, right?
Yeah.
So do we need to calculate the probabilities of all the data, or we just have one data and then we can prove them?
So what you have to do is you have to think about what does it mean that 2 distributions are the same?
All the data generated have the same probability.
That's one way. What is a these are 2 functions, right? So when are 2 functions the same?
They have the same parameters.
I don't know even how they are written. How do you know that? So there's a box here and there's a box here. Inside these 2 boxes, there are functions. How do you know that these 2 functions are the same? You don't know what's written inside, but you can test.
Do you mean like I give a lot of data and test the
This would be one way, right? So you'll basically take a data point, ask this box, what's the value that you give me on this? Ask this box, what's the value that you give me on this? If it's the same on all the data points that you give, then it's the same function. And basically that's what you have to do here. But instead of giving a lot of data points, there's one data point that you can give. There's one thing that you can do that will indicate that the probabilities are the same, right? If the joint probability is the same here and here, so you have to write the joint probability distribution. If you can write the joint probability distribution here and here, it's the same.
The joint probability distribution, do you mean the probability of A, B, C, D?
Yes, that's the joint, right?
Okay, so we need to prove that probability of A, B, C, D is the same from here.
General way, but yes. Yes. Sure, thank you.
Oh, no way. That's awesome. For a product manager. Very cool. So you would apply for product manager? That's actually what I'm using, just have an Excel file.
Professor.
Hi. Just a second, I have to finish something.
Yes, sir.
Yeah.
Professor, I just have a doubt in the syllabus. Like in the syllabus, when I checked, like last week, below Bayesian networks, there was some PCA. I mean, not PCA,
Yeah,
dimensionality reduction, and
The most, but I didn't get there.
so we are not doing that.
No. Didn't manage to get there.
Okay, sir.
Next year.
Thank you, sir.
Sure.
And just one doubt, like, is the k-means clustering similar to this k-means we did from the EM algorithm?
Yeah. Yeah. So in the class, I discussed the differences between kind of the commonly used k-means clustering and the one that we derive from EM. Very similar algorithm. In fact, the commonly used k-means is what I called hard EM. So it's basically the same algorithm, only that you don't keep the distribution, you choose just the mode of it.